Hello students, welcome to this new module in this course on mathematical methods in chemical engineering, CHE 641 taught at IIT Kanpur. In this module we are going to review and learn some new things about complex numbers and complex analysis. Okay, so let me begin first by saying that in chemical engineering especially, complex numbers are used widely in process control, transport phenomena and fluid mechanics especially. So it is very useful to have a good grip on the fundamentals of the ideas and important general results in this area of complex numbers and complex analysis. In addition, it is also very useful, the notion of complex numbers and functions of complex numbers in subjects like linear algebra that we are going to shortly discuss in the future modules, and therein you will see that complex numbers are used in Fourier series, Fourier transform, Laplace transform, and so on. So this is very fundamental. So although many of you would have had some exposure to complex numbers, I thought we'll have a quick review or recap of the same so that all of us are on the same page while we go along in the course. Okay. Now, what is the need for having complex numbers? Right? This is something that you might wonder. Why do we need complex numbers? Right? So let's consider simple quadratic equations like this. For example, z squared minus 4z plus 5 equals 0. Okay, let's say this is a quadratic equation that you want to solve. Of course, you can factorize it and write it as z minus z1 times z minus z2 is 0, where z1, 2, the two roots are given by the quadratic formula, which is 4 plus or minus square root of b squared minus 4ac is 16 minus 20 upon 2a, which is 2, and you will find that this is nothing but 2 plus or minus square root of minus 4 upon 2. Okay, so you will end up in having to deal with, while solving quadratic equations, you will end up to having to deal with square root of negative numbers, and that is indeed the origin of okay, so how do you deal with such things? That is indeed one of the origins of having to generalize to complex numbers. Okay, this is not very much unlike solving simple linear equations. Suppose I say x minus 4 is 0, you will, if you are aware of only positive integers, you will say the answer is x equal to 4. Suppose I ask you the question, what is x plus 4 equal to 0? Unless you generalize the number system to negative integers, right, then you will not be able to say the answer is x equal to minus 4. In the same way, so you are able to generalize the numbers from positive integers to negative integers, and then to rational numbers to irrational numbers, and so on and so on. In the same way, complex numbers are a natural way of generalizing real numbers to include things like square root of negative integers or negative numbers in general. Okay, so you say what we do is you write minus root 4 is equal to square root of root 4 into minus 1. We write this as square root of 4 into square root of minus 1. So any square root of a negative integer or a number can be written therefore as in the following sense, that you can write it as if you have any square root of minus a, you can always write it as square root of a times square root of minus 1. So the square root of minus 1 seems like a fundamental entity in order to deal with square root of negative numbers. So that is given a special symbol in complex numbers that is called I, the imaginary unity. Okay, I is denoted as square root of minus 1. Okay, so with this, and then of course we will develop rules for dealing with this this new imaginary quantity called I. This is called the imaginary unity. Okay, now so we can write, therefore, in this expression, oops, I'm sorry about this. Okay, so let me back up a little bit. Yeah, okay, so here, so we can write in this expression, this can be written as 2 plus or minus square root of 4 into square root of minus 1 upon 2. Square root of 4 is 2, so this will cancel with this, so this is nothing but 2 plus or minus I, because square root of minus 1 is I. So these are the two roots. Okay, for this equation, the two roots are z1 2 is equal to 2 plus or minus I. So because we are able to now generalize our notion of square roots to even negative numbers, we are able to write it. Okay, so now let's take a new sheet. Okay, now when you have 2 plus I or 2 minus I, you have two parts to this number. Okay, this part is called the real part of this number, and this part is called the imaginary part. The part containing I is called the imaginary part, and the total number is called a complex number, just to differentiate it from the idea of a real number. Okay, so in general, a complex number is written as Z is often denoted by the number the letter Z is written as X plus I times Y. X is called the real part and Y is called the imaginary part. The imaginary part is multiplied by I. So the imaginary part of a complex number itself is a real quantity. The imaginary part is not complex. Okay, by definition, imaginary part is the one that multiplies I. So you will always you have the fact that imaginary part is actually a real quantity. Okay, so notation, usually the imaginary unity is often denoted with I. That's what I'm going to use. But in some textbooks, especially the ones that deal with electricity and magnetism, they use J also. So you should be just aware. So in this course we will use, and the books that I have prescribed often use this, but if you deal with electrical circuits and so on, where I is denoted for current, so in electrical engineering I denotes current, so there they will use J for imaginary unity. Okay, so what is a complex number? Therefore, a complex number Z is X plus I Y. So you can think of this as an ordered pair, because you have two components, real and imaginary. So you can imagine writing this in terms of let me just draw a line, a coordinate system, where this is the real part of Z, where you plot in the x-axis, or the abscissa are the real part, and in the ordinate you plot the imaginary part of Z. Okay, so you can denote any point x, y in this plane. Okay, so the complex number can be represented in a plane, and such a diagram, such a plane is called an Argand diagram sometimes, and this is also called the complex plane. Just as you have the real line in natural numbers and real numbers, so you have in order to describe a complex number, you need a plane, because a complex number has two entities, the real and the imaginary. Okay, All right, so now how do we add complex numbers? So if you have two complex numbers, z1 plus z2, where z1 is x1 plus iy1 and z2 is x2 plus iy2, then in order to add two complex numbers, you have to add the real parts plus I times the imaginary parts. Okay, it's very simple. Okay, so that is how you add complex numbers. Of course, you can try and give a geometric interpretation as well, like so. Suppose you have this complex plane. Okay, now I call a complex number here as z2 and then another complex number here as z1. Okay, we can use a straightforward vector like addition, and then this the line joining the origin and this line is the answer z1 plus z2. So let me write down the three numbers. This is z1, this is z2, this is z1 plus z2. Okay, now we can call this z3 as z1 plus z2. Okay, so this is something that you can do. So if you want to worry about the rules that addition of complex numbers follow, it is commutative. Z1 plus Z2 is Z2 plus Z1, and it is associative. Z1 plus Z2 plus Z3 is equal to Z1 plus Z2 plus Z3. So the usual rules of adding and subtracting, they all. So this is whenever I write the complex, whenever I draw the complex plane, the real part is the abscissa and the imaginary part is the ordinate. Okay, now there is a very important thing that you have to understand about complex numbers, and that is with regard to the what is called the modulus and argument. Oops, I'm sorry about this. Of a complex number. Okay, now that you have understood that a complex number can be represented as a point on a plane, complex plane, right? So this is a complex number with real part x and with imaginary part y. This is real, this is imaginary, right? Now you can join the origin to the number, sorry, the point that represents the number z. Now the distance from the origin is something that you all know from Pythagoras. This theorem, this is denoted by the letter R, or it is also denoted by this symbol, which is called the modulus of the complex number z, is nothing but square root of x squared plus y squared. Okay, so this is something that you know from Pythagoras theorem. So that this is called the modulus of a complex number, or the absolute value of a complex number. Now you can also, of course, describe in terms of an angle theta made by that line joining the origin to the point with the x-axis or the real axis. That theta is of course given by tan theta is equal to y by x. So theta itself, okay, can be thought of as tan inverse of y by x, but there is a small catch, as I will tell you. So right now I will say theta is almost equal to. I will qualify this in a few minutes, because you have to worry about not to fix the angle, you have to worry about the quadrant in which the point is there in the complex plane. So we'll come to that in a few minutes. Okay, so now let me take a new sheet. Oops, I'm sorry about this. All right. So if I have, again let me give an example. If I have a number z is from the origin. Let's say this is this is 1 plus I. Oops, sorry about this. Let me just check this. Let's say this is the point 1 plus I. This is the real axis and this is the imaginary axis. Okay, so z, let's consider the complex number 1 plus I. Then you will say tan theta. Well, first of all, mod z is square root of 1 squared plus 1 squared is equal to root 2. Right? Now what is the argument? Tan theta. Tan theta is y by x, which is 1 by 1 is 1. So because this theta lies in the first quadrant, you know the point lies in the first quadrant, you can ascribe theta is equal to 45 degrees or pi by 4 radians. Okay. On the other hand, suppose you have a point here. Let me take a different color. Okay. Okay. Now suppose you have a point here, and that point has coordinates -1, -1. Okay. Let's say this is -1 minus I. Oops, I'm again sorry about this. Let's say this is -1 minus I. Then let's consider this complex number -1 minus I. Then mod z is again, I'm sorry about this, just quit this. Mod z is again root 2, whereas theta, now you have to be a little more careful. So what is theta? Theta is always measured, what is the angle made by the point, by the line that joins the origin and the point with this x-axis. So you have to measure theta for this particular point in this sense, right? This is theta. You cannot say because tan theta, here also tan theta, let me erase this a bit. Okay, here also tan theta is nothing but -1 by -1, which is 1. You cannot write theta as 45 because you have to account for the fact that this point lies in the third quadrant. So what you have to do is, you have, this is 180 degrees or pi radians, and from here it is another pi by 4. So you have to say theta for this point, theta is pi plus pi by 4. Okay, this is nothing but 5 pi by 4. Okay, so now there are multiple ways of deciding on the angle. So here I have measured the angle in the counterclockwise direction, and angles that are measured in the counterclockwise direction are always considered positive. Instead, if you were to find the angle made by this same line from the origin to this point, okay, in this fashion, you go in the negative clockwise direction, which is negative. Now this answer will be -3 pi by 4. Why is that? Because you have a pi by 2 here, right, and then you have another pi by 4 here. All right, so that if you add up, it is see, pi by 2 plus pi by 4 is nothing but 3 pi by 4. But you also have a negative sign because this is a angle that is measured clockwise, negative angles, whereas counterclockwise is positive angles. Okay, so this is one and the same, but you can represent it in either way. Okay, so you can also consider other examples wherein you have z is -1 plus I. Here again mod z is root 2 because that's the same, but tan theta is 1 by -1, which is -1. And if you look at the complex plane, -1 plus I lies here. Okay, So you are interested in this angle theta. So this is nothing but pi by 2. This pi by 2, this is real and imaginary and so on. This is nothing but theta is pi by 2 plus pi by 4, which is 3 pi by 4. Okay, and similarly you can consider z is 1 minus I, and right now if it is 1 minus I, the point is here. Let's use a different color. So the point is here, placed here. Now you have to come all the way here. Okay, from here all the way you have to come here to measure theta, and if you do that, you will find that this is pi by 2 pi by 2 pi by 2, which is 3 pi by 2 plus pi by 4. Okay, so theta for this problem, for this point, is 3 pi by 2 plus pi by 4, which is 7 pi by 4. So this is how you ascribe angles. Usually you ascribe it in the counterclockwise direction. So you will consider the complex plane theta will then range from 0 to 2 pi. Okay, the range of theta will be from 0 to 2 pi. On the other hand, you can also decide to have theta from minus pi to pi, in the sense that for points on the upper half you will use the counterclockwise measurement, that is positive sense of measuring angles, and the points on the lower half you can measure it in the negative sense. Both are equivalent. Nothing will change. It's just a convention you have to agree to, and then stick with that in the rest of your calculations. Okay, right. So this is the sense in which I try to mention, if you write z is x plus I y, and then mod z is x squared plus y squared to the half, then argument of z, I said, is almost equal to, in the following sense, because tan inverse of y by x, because this is almost equal to is because you have to account for the quadrant in which the point lies. Okay, so this is very important while writing the modulus and amplitude of a complex number. Okay, so there is another important idea about modulus, the argument of a complex number. The argument of a complex number theta is only defined up to a factor of additive factor of 2 pi. Sorry about this. Why is this? Because if you have a complex plane, let me just use a line. If you have a complex plane, and if you have a point on the complex plane, okay, so this is theta, right? This is the angle made by this with the positive x-axis in the counterclockwise sense. Now if you go around all the way and then come back to the same point, so you will go, the angle measure will be theta plus 2 pi, but you are at the same point still. So you can always add 2 pi, and that will also refer to the same point in the complex plane. Okay, so this is something that is very important. As you will see, this leads to some fairly interesting and subtle aspects to multivalued functions as we go along. But remember that you can always define theta only up to a factor of 2n pi, where n is an integer. Okay, so this is something that is very important. Okay, the other thing, let me take a new sheet. The other thing you should remember is that in complex analysis you have to often deal with angles. So here angles are often measured in radians as opposed to degrees. Okay, that's because many times we will have to use relations like d dx of sine x is equal to cosine x and so on Now here these kind of relations are correct only if x is measured in radians, not in degrees. So you know that 2 pi radians is one entire circle 360 degrees. So pi radians is 180 degrees. So this is how one converts between degrees and radians. But remember that you cannot use radians if you have Taylor expansions, or if you have calculus like derivatives. You can use degrees for adding and subtracting an angle, right? But not for expressions involving calculus. So for example, you might know this result 0 to 1 dx by 1 plus x squared. We write this as this is nothing but tan inverse of 1. This 1 is in you have to write the answer in radians. Tan inverse of 1 is pi by 4, and you cannot write this as 45 degrees. Okay, this is completely wrong. Okay, you have to write the answers in radians. So when in doubt, use radians, you will not go wrong. Although sometimes intuitively we know that degree is is much more convenient to think intuitively, but we should while calculating, it's always useful to use radians. Okay, all right. Now, as I told you, theta, the argument of a complex number, is defined only up to a particular let me see. You can always add 2 and pi to the argument of a complex number where n is an integer. 0 I'm sorry, the software crashed. I will stop here and then I will continue in the next recording.